Hi, my name is Hsiao. I am really honored to be here to introduce my research. I know some people have the customization problem of the design build process, especially we also have limited funding and time. I will show you the presentation and deliver the inspiration of the possible solution about this. In the project, we have 10 days and for the design and 3 days to finish all the construction. Moreover, we only have $1,200 funding for the construction fee. So how do we achieve the target? First, I will show you 7 issues causing the customization problems, then how we create the collaborative communication workflow to approach the goal. Okay. Now that the numerical control machine such as CNC or the robotic arm embodies the subtractive manufacture methodology, this device can leverage any number of tools, including drills and saws, to whip away a large amount of raw material and create prototypes or finished product at scale. While the numerical machine has some manufacturing limitation, this feature and the subtractive workflow, their power are applied broadly across numerous industries. However, while subtractive manufacture can certainly generate quality products at accelerated pace, but it also creates certain considerable waste. According to wiki definition, waste is unwanted or unusable materials. In other words, waste is any substance discarded after primary use or is worthless, defective, or of no use. On the page, we list 7 wastes produced in our project's life cycle. To summarize, saving waste means saving funding and time. This diagram reveals the new symbiotic relationship between academia and the industry. We know that the association relies on the connection between the modeling method and the fabrication strategy. Traditionally, the pavilion modeling methodology always applied the parametric tool in seeking the hypersurface design. Likewise, the fabrication strategy focuses on the technique to manufacture the highly complex geometries. The close connection between them is the key to tie manufacturing control and ensure construction accuracy. However, to solve the parametric design would raise the sustainable issue of overly waste the material in the manufacturing process. Thus, we attempt to redefine the manufacturing experience via the application of machine learning and look forward to revealing the new relationship between the algorithm design and the sustainable issues. In 7 ways of our project, waste can be divided into 3 items: the waste of time, the waste of overprocessing, and the defective materials waste. In the project process, we always spend time waiting for an answer from other departments, or rework for the amendment, or waiting for the supplier's delivery. This waste always disrupt the workflow. To deal with the issue, we need the workflow accelerator to avoid the time waste. In our project, we choose machine learning as the accelerator in our workflow. Why do we call machine learning is the accelerator in the workflow? It is because the project relies on a massive workload of the data calculation and the tricky generation of the form finding. We believe that AI or the machine learning algorithm allow real-time computation and assist project in creating a more optimal design. Particularly, we adopt ML algorithm, a Spec and TensorFlow to drive AMD CPU for the high performance computing. In our research, we use neural style transfer to process accurate and complex spatial generation. Based on the usage of neural style transfer, we need to prepare two kinds of the material for machine learning, including the content image and the style image. For the terrain generation, we use the satellite map provided by Google Earth. However, we still need to design the form finding algorithm to produce the style image. We use different color mode and working distance to generate the style image that can contain with 5 major features for machine learning in generating terrain and space. Originally, neural style transfer refers to the algorithm processing the stack of image transformation. Our research attempt to refer it to the algorithm deal with the series of spatial element reconfiguration. The process of spatial reconfiguration is based on the content image context. Thus, we provide the style image, including 5 spatial features and 2 geometry labels, to enable the VGG16 model that can deal with the regularity transformation. To observe whether neural style transfer can deal with regularity transformation via the style image, this page we try to relocate the entrance to different places and plot different configuration style image. Obviously, based on the condition given by the style image, we can perceive the neural style transfer can produce different entrance form on site, even the path, the territory, and the density. When we look at the residential cluster on the content image, which is showing on the left side on the page, we also can recognize them on the explore image, which shows on the bottom of the page. That means it is possible to extend the concept of neural style image as a space transfer. But we still need to do more research to verify this kind of the concept extension. By applying machine learning, we have proposed different schemes. By applying machine learning, we have proposed different schemes to discuss and determine the form of the terrain-like pavilion with the committee within 2 days. However, the terrain-like pavilion arises a huge specific data that we need to take a couple of time to match it with the material specification. To prevent it from triggering scheduling complication, delays, and so forth, we need to create appropriate small machine where they are needed in the workflow. It would be helpful for the workflow processing. First, we need to create a small bin algorithm to sort the data and classify the number to match the material specification. Based on the terrain-like pavilion structure, we classify the number into 7 kinds of the items. And the construction fee is calculated as $1,380. If we consider the waste and the defective material, the price will be higher than this. However, we only have 1,200 funding for it, so we need to think another way to optimize the data in saving the funding. The length of the CLT panel supplied by the supplier is 4 meters, and the wood sheet is 5.7 meters. We use Excel server add-in to find the optimal pairing values matching CLT panel length based on the material specification. We can reuse the maximum surplus materials through the pairing process and purchase the minimum amount of the material. After the pairing process, we get the material theoretical value, which is 6.6% of the total materials weight. However, we still cannot achieve the goal of the construction fee. We need to think about the other method to save the price. In 7 wastes, the waste of defective material is the most obvious one. Normally, it requires rework or replacement. It not only wastes time, but also wastes the resource. Considering the tight schedule and the limited funding, we need to prevent the increase of the cost due to the rework and the replacement. Therefore, we accepted the defective material to prevent the cost increase and get a better price from the supplier. When we received the supplier's material, we found a shearing, splitting, crushing failure. Fortunately, we still can assemble most of the defective material if we can assemble them to meet structural behavior. After the optimal data pairing, we purchased 10 pieces of faultless CLT panels as primary structural columns, 68 elements of defective CLT panels as secondary structural material. Through data pairing and adaptive assembling, we reduced the price successfully from $1,380 to $1,043. According to the data shown on page 13, we can mark the numbering on CLT panels. Then students can assemble defective and faultless material as 16 pieces of structural frames. Actually, we did some rework on it due to the quality control on sewing defective materials. And we spent 2 days working on this step. After establishing 16 structural frames for the terrain-like pavilion, the most difficult construction is to top the wood sheet on the pavilion's roof. The supplier's longest wood sheet is 5.7 meters. However, the supplier cannot offer enough quantity of 5.7 meter wood sheet. Thus, we need to purchase another kind of material specification. So we choose to purchase the wood sheet in 5.1 meter as the complement. However, the longest axis of the pavilion is 11.5 meter. We need to consider how to join two. We need to consider how to join two wood sheets to meet the requirement. After discussion with the structural consultant, we use 5.7 meter wood sheets to construct the stronger roof bottom structure, then we can pin the shorter one on it. Therefore, we create an optimal cross bracing structure algorithm to find the solution for the roof structure, roof construction. On this page, we compare the rigid grid pattern and the random crossing bracing pattern. According to the algorithm calculation, the rigid grid pattern uses 34 pieces of 5.7 meter wood sheets, and the crossing bracing pattern uses 47 pieces to constitute the roof bottom structure. It means that the bottom of rigid grid pattern needs to support more weight than the random crossing bracing pattern. Also, a rigid grid pattern cannot match the material specification. It means the grid pattern will generate more surplus material than the random crossing bracing pattern. And it is very interesting because after the exhibition closed, when we start to, it's very interesting when we finish the construction, there is a gardener come here to ask us to collect all the surplus material from the surplus material and reuse it as rough sawdust. It is good material used for the soil's water retention in the gardening. So we don't generate this kind of the waste material from the wood sheet. Actually, we did not have time to train the students. All the students do the pavilion without the construction experiments. That is why we use collaborative computation method doing on-site management. The program can produce the library that the student can mark it on the material. Then the student can follow the library to assemble the material. Moreover, if one of the algorithms has technical difficulty, that won't trigger scaling complication delays and so forth. In the beginning, we did not have the confidence that the pavilion can get over 3 months exhibition because we have a very heavy raining season in the period of the March and May in Taiwan. Especially, we use a lot of the defective material to get the good price from the supplier. After exhibition closed, the pavilion still stands in one piece. Even students can disassemble and collect all the material for their final undergraduate exhibition in June. This is a tough project and research because we don't have time to verify the hypothesis. The only way we can prove is waiting for the exhibition close. If the pavilion is damaged during the exhibition period, the research will suffer the serious risk. Fortunately, it proves the research hypothesis by real action. We believe the collaborative computation is the next tendency, and it relies on the clear goal and workflow definition. Then we can create a toolkit to achieve the purpose. It seems that we learn a lot of the tools, but the most important thing is we need to think about how to discover and how the different tools can cooperate together and work for a specific purpose. Thank you for your attention.